So Unit C continues our travels through the world of algebra in this course and steps it up. So to this point, we've been dealing with linear equations and linear inequalities. In Unit C, we're going to bump it up so that we're going to deal with systems of linear relations or linear equations and linear equalities. So systems of linear equations or qualities is really just two or more equations. And so in this, we have things that we've seen already, right? Except for we're going to consider them together. We're going to consider them as a pair, and we're going to see how they relate to each other. The solution to this could be one of three different things, and that's where the notes are going to start for us today. So one option when you consider a system of equations is that if you were to graph those two equations, and you put one line on the graph and the other line on the graph, they may intersect at a particular point. That point is super important because that point of, say, 2 and 1 in this case is the values of x and y that satisfy both the equations, makes both the equations true. And so each one individually would have an infinite number of ordered pairs that make it true. But when you consider them together, when you consider the system of equations, there's really only one x and one y that satisfies both of them. So what happens when we see them on the graph is that we see the two lines intersect at that point. That point, x and y, is the solution to the system. We would say that the system is consistent, and there's a unique solution to it. It's the sweet spot, if you will, that satisfies both the equations, makes them both true. An infinite number of ordered pairs that make it true. This is what happens when you have two equations of a line, and they may look different from each other, but if you were to graph one on the graph, it would look like that. And then if you put the other line on the graph, even though it looked different, it actually makes the exact same line. So we can have two linear equations that look differently, but when we graph them, they're actually the same line. They're the same graph. And so we would say that this system is dependent. Just like any one individual linear equation, it has an infinite number of solutions. So there's an infinite number of ordered pairs or solutions that would make this happy. We say that is a dependent system. So funky words for these. Conceptually, we can see the picture. So we have consistent, we have dependent, and the third option is if you're considering two linear equations at the same time, you can put them on the graph and they may run parallel to each other. If two, those don't look super parallel, so if they run parallel, it means that they have the same slope. This means that those two lines are never going to meet. They're never going to intersect each other. There is no solution to this system. So no solution, because there's nowhere that the same x and y is going to make both equations happy. And we'd say that that system is inconsistent. So you have these funky words, consistent, dependent, and inconsistent, and then really the practical bits that go with them. So for a consistent system, the two lines intersect at a point, x and y. For a dependent system, the lines are actually the same line, and so there's an infinite number of ordered pairs that would make those equations true. And for an inconsistent system, the lines may look different. What they do share is the same slope. They run parallel to each other, and so that means those two lines are never going to intersect. There is going to be no solution to that system that actually satisfies both equations at the same time. So these are the three sort of conceptual options for systems of linear equations or linear relations. And we're going to move on, and the first part of this is solving systems through graphing. So it really does reinforce kind of the concept of what we're doing here. So to solve by graphing, we're going to put the equations into slope-intercept form. You could do it with table method or intercept method, but I think slope-intercept formed is the most efficient way to graph a linear equation. And then we're going to state what the solution to the system is. Is it consistent? In which case there'd be an x and a y. Is it dependent? dependent, in which case there's an infinite number of solutions? Or is it inconsistent? Are they actually parallel lines, so there is no solution? And those are really your three options when you consider systems of equations. So let's do these ones, solving by graphing. I'm going to put this first equation into slope-intercept form. I'd have y equaling negative x plus 6. That tells me that my intercept, my y-intercept, is 0 and 6, and my slope is negative 1 over 1. So I always start with the intercept, so I'd go to 0 and 6, and then my slope gives me the instructions to another point on the line, so go down 1 and over 1. And I could go down 1 and over 1, and I'm going to go more because you know how bad I am at drawing these lines. Oh, maybe. Oh, not so bad. Okay, and now I'm going to deal with the other equation. So the other equation I'm going to put in slope-intercept form. I'd have negative y equaling negative x plus 4. Pesky negatives, I'm dividing both sides by negative 1 to say that y equals x minus 4. So interpreting this, my y-intercept for this second equation is 0 and negative 4. That's an ordered pair, that's a location on the graph. And then my slope is the instructions to get to another ordered pair on the graph. So that's 1, or 1 over 1. Can't even see anything on that x. So putting this on the graph, I'd start at my y-intercept and then use that slope to go up 1 and over 1, finding more points on the line. And I'm going to do that a whole bunch of times because you know how bad I am at drawing these lines. And where these two lines intersect is going to be the solution to my equation. So right there, that's the answer. That's the x and the y that makes both of these equations true. So my answer for this system is that it's a consistent system. And the answer would be 5 and 1. Let's try another one. We really do use a lot of the skills that we've been doing before. So, you know, it does help reinforce this concept of the slope-intercept form and more of that algebra. So we're going to start on this system by the first equation, solving for y. So subtracting x from both sides, I get negative 2y equaling negative x plus 4. Divide by negative 2 on both sides. I get y equaling some funky business here with the fractions. I'd have a positive 1/2 x minus 2. So my y-intercept would be 0 and negative 2, and my slope is going to be 1 over 2. So let's put this one on the graph. Let's finish it up. So 0 and negative 2 is my y-intercept, and then I'm going to go up 1 and over 2. Up 1 over 2 to put this equation on the graph. Whoa, I hit all 3 points. Okay, let's deal with the next equation. So the next equation, I'm going to do the same treatment, right? I'm going to start by subtracting 2x on both sides of the equation. That would give me negative 4y equaling negative 2x plus 8. Divide by negative 4 on both sides. That gives me y equaling, if you need to do the fraction math in a separate place or way, then do what you need to do. I get positive 1/2 x minus 2. You may notice something about the two lines in slope-intercept form. Up above and at the beginning, they looked really different. But once we do our algebra with them, once we put them in slope-intercept form, you can see they're actually exactly the same pieces of information I'm pulling out. They are the same line. So I've got the same y-intercept and the same slope. So I could try this again, right? Two lines in the exact same place. This is a dependent system. There are an infinite number of solutions. So we would have, you know, an infinite number of ordered pairs that actually satisfy both these equations at the same time, because even though they look different, they are actually the exact same lines. So one more, and you might guess which option this one is. I'm going to pretend I don't know what it is. I'm going to walk into this in the exact same way. I'm going to treat each one of these by putting them into slope-intercept form. This is my favorite way of putting them on the graph. So I'd get y equaling negative 2x plus 2. That tells me that my y-intercept is 0 and, oops, that's really messy, plus 2. And my slope is negative 2 over 1. So again with this, my y-intercept is where I'm going to start, and then my slope tells me to go down 2 and over 1. And I could do that a few times, especially if I don't have a ruler, or if I'm using this funky tablet to, oh, I am having a good day with the lines. Okay, let's do the other equation. So the other equation, I'm going to put it in slope-intercept form. I'm going to start by subtracting 2x from both sides. That gives me y equaling negative 2x plus 4. And now I can interpret this like I did the other. So my y-intercept is 0 and 4. And my slope is negative 2 over 1. Let's put this on the graph. So I'm going to go to 0 and 4 as my y-intercept. And then my slope tells me from that point, go down 2 and over 1. Down 2 over 1. If I draw this on the graph, oh wow, I am having a decent day with drawing lines. I actually have the same slope. The lines run parallel. And so what that's telling me is that there is no way to make this system of equations happy. There's no value of x and y that's going to satisfy both equations at the same time. So in math, I say that this is an inconsistent system, and there is no solution. So just as a reminder, those are 3 of the examples. In the Moodle site, there are note keys for you that are much neater than what I'm about to do in the video. If you want to switch and use those, or even just pause this video so you can see the remaining note keys for this unit, go ahead and do that. That might be most efficient. I'm going to keep talking through in case you're somebody that wants a little bit more of a guided tour. You want to hear the explanation of each of these. So I'm going to move on in the video here, putting each of the equations in slope-intercept form in these systems. So for D, I'm going to start by subtracting 3x from both sides. That would give me y equaling negative 3x plus 6. My y-intercept would be 0 and 6, and my slope is negative 3 over 1. So putting that on the graph, I'd have 0 and 6, and then my instructions tell me to go down 3 and over 1. Down 3 over 1. I can do it one more time. And I'm going to try, again, if you want neater lines, go to that answer key where I used a ruler. I'm going to put the second equation now on the graph. I'm going to put it in slope-intercept form. I'd have y equaling negative x plus 4. When I interpret this, that tells me my y-intercept is 0 and 4, and my slope is negative 1 over 1. So putting that on the graph, I'd start at my y-intercept, down 1 and over 1, down 1 and over 1. If I see, and I use that slope sequentially, which really helps me, I've got one point where these 2 lines intersect. That point right there is going to be my answer. And so my answer for this one is 1, 3. You could say that it's a consistent system if you want to reinforce that in your mind. But the things that I'm putting the boxes around are probably the most important to get as your answer. All right, let's move on and do another one. Lots of practice here. You'll see how much we reinforce this, algebra, the solving for y that we've been doing all the way through the last couple sections and chapter. Okay, dividing by negative 1 on both sides, I get y equaling a positive 2x minus 4. So that tells me my y-intercept is a point, 0 and negative 4, and my slope is a 2 over 1. So let's put that on the graph. Let's finish this one up. So 0 and -4. And then I go up 2 and over 1. 2 over 1. Just double checking my key that I hadn't made a mistake. Oh, that's really not a great line. Supposed to be a straight line. Use your imagination. I'm going to carry on. Hopefully I have better luck with this second equation. Start by subtracting 2x from both sides. I'd have -y equaling -2x plus 6. Divide by -1 on both sides. Y equals 2x minus 6. At this point, you may see that they have the same slope, but let's just, you might not see through to the answer. I don't think that's a good strategy to just have to be able to know what the answer is. So let's take our time and give these equal treatment so that we can put them on the graph. So I'm starting at my y-intercept of 0 and -6, and my slope gives me instruction to other points on the line. And so I could put a few on there. Perfect world, I'd have a ruler. Oh, this is terrible. Again, remember I did that answer key nice and neat. We should have two straight lines that go on forever that are parallel to each other. And so that, in a nutshell, is an inconsistent system. And really, there is no solution, right? That would be my answer, because that's what happens in an inconsistent system. So the next side of the page, we have 3 more. These ones get a little bit tricky in that they have these funky ones where x equals a number and y equals a number. We're getting pretty used to doing the hard ones. And like this first equation in this system, putting it in slope-intercept form gives me some stuff to interpret, gives me some stuff to put on the graph. So I get it in slope-intercept form at y equaling 2x minus 6. My y-intercept for this guy would be 0 and -6, and my slope would be 2 over 1. So y-intercept down here, and up 2 and over 1, up 2 over 1, up 2 over 1. Doing a few like this is really my way of covering my bases for doing really messy lines. So there we have the first one on the graph. This next one is a line at x equaling 2. It was one of those funky ones where it was either a horizontal or vertical line. If x equals 2, that's going to be a vertical line at x equaling 2. And this gives me the picture to see where these two intersect each other. And so the answer for this one is going to be a consistent system. And the solution would be 2, -2. That would be the value of x and y that we could plug in and make this system true, make both of these equations true with just an x and just a y. Another one, just 2 more on this page. Putting them in slope-intercept form, rearranging to solve for y. Do you remember how hard this was the first time you tried it? And then doing the interpretation of this. So once it's in slope-intercept form, that tells me that my slope, or my intercept is 0 and -4 for this guy. And my slope is a very invisible 1 over 1, a +1 slope. So my y-intercept's down here, and then my slope is going up 1 and over 1 all the way. I'll try really hard to hit all those lines. Could be worse. And now I'm going to treat the second equation similarly. So I'm subtracting 2x from both sides. I'd have -2y equaling -2x plus 8. Divide by -2 on both sides. I'd get y equaling, lots going on over here. -2 divided by -2 is a +1 or just an x. You can put a 1 in front if you want. Minus 4. So these look really different, but they are the same line. When we solve them for y, that allows us to do the interpretation of them with slope-intercept form and see that they're actually very much identical. And so I'll spare you the messiness, well, I'll try. Do it again. I can go up better than down on this. So I've got this situation is a dependent system. There's an infinite number of solutions. At this point, you're probably getting pretty good at putting these on the graph. Remember, what we're looking for is the final answer, the things that I've been putting in the box. If you put consistent, dependent, or inconsistent down, that's great too. But that's what we're really trying to roll together here. So the last one, the oddballs, the ones that are deceptively complicated in their simplicity, this is going to be a line at y equaling -2. This is going to be a line at x equaling 3. And so if I put those on the graph, I can see there is a point where they intersect. I can see that it is a consistent system. So it's consistent. There is a unique solution. And that solution is going to be at the point 3 and -2. So that does our first treatment of these systems of equations. They're solved through graphing. The next couple sections of our notes, we're going to go through and solve systems with an algebraic approach. So I really like the pictures. I think they give us a good foundation. And again, yeah, if you want nice, neat lines, remember you do have that answer key to my notes. It could be useful.